Hello everyone. In this pre-lecture tutorial, we're going to cover one of the fundamental skills of chemistry. We're going to learn how to balance chemical equations. And so, if you recall, we have discussed the law of conservation of matter earlier in the year in class. And so, the reason why we have to balance chemical equations relates directly to the law of conservation of matter. Because, as we're aware, matter cannot be created or destroyed. And so that has certain implications for the starting mass and the ending mass of matter involved in a chemical reaction. Those two masses must be equal. But it is also true that the numbers of each types of atoms involved in a chemical reaction equation must also be the same as each other. Otherwise, for example, if you take a look at this first reaction equation that I have here on the slide, if you look carefully, basically there's only one chlorine on the reactant side or the left-hand side of the equation, but there are two chlorines on the product side or the right-hand side of the equation. And so the way that we've written this chemical equation right now, it looks like there has been the sudden appearance of a chlorine atom from nowhere. And so that violates the law of conservation of matter. And so in order to adhere to that same law, then we need to balance our chemical equations once we write them. And so what you're going to find is the more of these equations that you do, the quicker you will become, and you'll be able to, on site, be able to quickly tell what you need to do to balance the equation. However, at first, if you're uncomfortable doing these, then I'll show you a method that is very basic that should make it easier for you to balance a chemical equation. And so let's begin doing that with this first reaction equation by writing out a table that contains all of the atoms that appear in this particular chemical equation. So I have zinc and sulfur and hydrogen and chlorine. And I'm going to create a partition in my table so that I've divided up the reactant side from the product side in the chemical equation. And I'm simply going to count the number of each type of atom on each side of the chemical equation. So if I look carefully, I have one zinc atom, I have one sulfur atom, as I said earlier, I have one chlorine, and I also have one hydrogen. However, on the product side, listing out the atoms again, I have one zinc, I have one sulfur, but I have two hydrogen, and I have two chlorine. And so, if you notice, the zinc and the sulfur are already balanced. The number is the same for each of those types of atoms on either side of the chemical equation. But the hydrogen and the chlorine, both of those types of atoms are out of balance. And so I have to find a way to balance them. Now, the only way that we can actually alter the number of atoms in a chemical equation is by inserting coefficients in front of each chemical formula. And these coefficients will multiply across the entire formula, similar to the distributive property in algebra. I cannot, however, mess with subscripts in chemical formulas. Those have to stay the same, so you're not allowed to change those. The only things that we can change are the coefficients. And so, if I take a look, I need to double my amount of hydrogen and chlorine on the reactant side. And so I can do that by inserting a coefficient of 2 in front of the hydrogen chloride in this particular chemical equation. Or in this case, probably this is hydrochloric acid. And so basically by putting a 2 in front of that hydrochloric acid, if I update my count, I now have 2 hydrogens and 2 chlorines, and now the hydrogens and the chlorines are now in balance as well, and the entire chemical equation is balanced. Okay, let's try one more. Let's try number 2 here. Once again, I'm going to create my table, and I'm going to count up the number of atoms on each side of the equation. I have one hydrogen, one chlorine, and one chromium on the reactant side, and I have 2 hydrogen, 2 chlorine, and 1 chromium. So again, in general, if something is in balance, like the chromium, you tend to leave it alone at first, unless it goes out of balance while you're trying to balance the equation. You don't touch it. And you work on the things that are out of balance first. And much like the first example, I have 2 hydrogens and 2 chlorines on the product side, but I only have 1 hydrogen and 1 chlorine on the reactant side. And so in order to balance out the number of hydrogens and chlorines, then I have to insert a coefficient of 2 in front of the hydrochloric acid as well. If I do that, then I will have 2 hydrogens and 2 chlorines on the reactant side as well as on the product side, and now the hydrogens and chlorines are also in balance, and the entire chemical equation is balanced. Now let's take a more complex example. Okay, so I have this equation. I have aluminum, I have iron, and I have oxygen on both sides of my chemical equation. And now I'm going to count up how many of each type of atom I have on either side. I have 1 aluminum, 3 irons, and 4 oxygens on the reactant side of this equation. On the product side, I have 2 aluminums, I have 1 iron, and I have 3 oxygens. So if you notice, pretty much everything is out of balance. And so let's pick a place to begin. Now, if you notice, probably the trickiest atom to balance here will be the oxygens, because I have 4 on one side and 3 on the other. And so that makes it a little trickier because there is no coefficient that I can multiply by, no whole number coefficient that I can multiply by on either side to balance this out. And so one thing that I find useful when I have that sort of situation is to look at the number of atoms on either side, and if you can't simply apply a coefficient on either side to balance, think of the least common multiple between the numbers of atoms on either side for that element. So I have 4 oxygens on the left and 3 on the right. The least common multiple between 4 and 3 would be 12 in this case. So I'm going to try to balance the oxygens by getting 12 on either side. On the product side, since I have 3 oxygens, if I multiply by 4, then I'll get the 12 oxygens that I want. But now I have to also update my count of aluminum. My aluminum count is now up to 8 on this side. If I take a look on the reactant side, again trying to shoot to get this least common multiple of 12 for the oxygens, I'd have to use a coefficient of 3, because the 3 would multiply by the 4 to give me 12 oxygens. And so I'd also have to update my iron count. Iron, there would be 3 times 3, that's 9 irons. And so now it's just a matter of balancing out my aluminums and my irons. On my product side, I have 8 aluminums. If I use a coefficient of 8 in front of the aluminum on the reactant side, then I'll also have 8 aluminums on the reactant side. If I take a look at my product side, if I use a coefficient of 9 in front of the iron, then I'll also have 9 irons on the product side. And if you notice, the numbers of each type of atom are now the same, and so that means that my equation is balanced. All right, one more example here. All right, if I have this reaction, only 2 atoms apiece, then basically I have 2 hydrogens on the reactant side, 2 bromines on the reactant side, but only 1 of each on the product side. So if I insert a coefficient of 2 in front of the hydrogen bromide on the right-hand side of this equation, updating my counts, I now have 2 of each, and now we have the same number of each type of atom on either side, and this equation is balanced. One thing to keep an eye on as you actually work on future equations to balance is that if you happen to have a common multiple or a common factor among all of the coefficients, you should reduce those down because, again, we want the simplest whole number ratio. One other thing I want to call your attention to is on occasion you will end up with fractional coefficients, in which case then we need to clear the denominator in those fractional coefficients. And so here's an example of where you'd have to do that. Let's set up our table once again. This reaction involves carbon, hydrogen, and oxygen. If I count up how many of each type of atom there are on either side of the reaction equation, I have 2 carbons, 6 hydrogens, and 2 oxygens on the left-hand side or the reactant side. On the product side, I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. Basically the 2 in carbon dioxide and the 1 that's associated with the water for a total of 3 oxygens on the product side. Now, I would have to go and think about balancing the carbon first, since it is out of balance. So I'm going to put a 2 in front of the carbon in carbon dioxide. So updating my atom count on the product side, I have 2 carbons, and now I have 2 times 2 is 4, plus 1 would be 5 oxygens on the product side. And I should also make some effort to balance my hydrogens. So I have 6 on the reactant side. If I use a coefficient of 3 in front of the water, then I'll have 6 hydrogens on the product side as well. But now I have to update my count for the oxygen. So 2 times 2 is 4 oxygens, times, or I should say plus, an additional 3 oxygens. That gives me 7 oxygens on the product side. Now, basically what that means is I have to insert some sort of coefficient that must be multiplied by 2, because diatomic oxygen has a subscript of 2. So if I want to count up the individual oxygen atoms, then basically I'm going to need to multiply whatever coefficient I use by 2, but I need to multiply some number by 2 to get 7. And so the only way I can actually make that happen is if I use a coefficient of 7/2. But I don't want to leave a fractional coefficient in a balanced chemical equation. And so to solve this problem, what I would need to do is multiply the entire equation that I have so far by 2, because then that would actually clear out the denominator of 2 in 7/2. But I still have to apply the factor of 2 to every formula in the equation. And so that would give me 2 C2H6 plus 7 O2 gives me 4 CO2 plus 6 H2O. And if we count on either side of the reaction equation, I have 2 times 2, that's 4 carbons on the reactant side. I have 4 carbons on the product side. On the reactant side, I have 2 times 6, that's 12 hydrogens. On the product side, I have 6 times 2, that's 12 hydrogens. And then oxygen would be 7 times 2, that's 14. But on the product side, I have 4 times 2, that's 8, plus another 6, that would be 14 oxygens. So if you notice, every type of atom has been balanced between both sides of the equation, and so this would actually be the balanced chemical equation for this reaction. So again, read through the book regarding the section where they discuss balancing chemical equations, and apply what we've discussed in this tutorial to the follow-up assignment, and we'll certainly go ahead and continue discussing this particular skill in class. Okay, so have a good night. See you then.